Hey guys, Mr. Backward here. In this video, we're going to look at the antiderivative part of the fundamental theorem of calculus. Now, the fundamental theorem of calculus is regarded by many as one of, if not the most important computational discovery in the history of mathematics. And there's actually two parts to the fundamental theorem. This video is going to focus on the first part, which some people call the antiderivative part of the fundamental theorem of calculus, but it's more widely known as the first fundamental theorem of calculus. So the first fundamental theorem of calculus says if we've got some function f that's continuous on an interval from a to b, then the function capital F of x, which is the integral from a to x of f of t dt, that capital F function has a derivative at every point in that interval from a to b, and that derivative of the capital F function, which is also the derivative of that integral, is just the function f of x. And it doesn't seem like much, but this is a really powerful conclusion that we're able to make. So it says that every continuous function is the derivative of some other function. So then every continuous function has to have an antiderivative. And it also says that finding a derivative and doing integration are just the inverses of each other. So here we're going to look at applying that first fundamental theorem. So we want to find the derivative of the integral of cosine of t dt from negative pi to x. And remember, the first fundamental theorem says that if we're doing a derivative of an integral of f of t dt from a to x, then we just end up getting the function f of x. So in here, our f of t function is really the cosine of t. So as we do the derivative of this integral, it just turns into the cosine of x. Essentially, what we end up doing is the derivative and the integral cancel each other out, but we replace the t with that x variable. Now we're also going to look at this one. So we're going to do the derivative of the integral of 1 over 1 plus t squared dt from 0 to x. So again, if we think about the derivative and the integral as canceling each other out, but replacing the t with an x, then we end up getting 1 over 1 plus x squared as our f of x function. Now in this example, we're going to look at this first fundamental theorem, but we're going to include the chain rule as well. So here we're going to find dy dx if y is equal to the integral of cosine of t dt from 1 to x squared. Now those first couple examples that we looked at, our upper limit of the integration was just a regular x, but here it's x squared. So we can actually think about our y as being a composite. If we introduce some new variable, let's use u to represent x squared, then we can really look at this y equation as being that integral of cosine of t dt from 1 to u, but because we're thinking about this as being a composite, we must apply the chain rule. So going back to when we learned about derivatives, if we had some function y being f of some composite u value, then as we do this derivative, as we do our dy dx, then as we differentiate the right-hand side, we get f prime of u, but then we also had to attach the derivative of whatever that u function was. So in here, as we look at doing the derivative of this integral of our cosine of t dt from 1 to u, the derivative and the integral are going to cancel each other out, but in this cosine of t, we're going to get rid of the t and we're going to replace it with that u variable. So this will say the cosine of u, but because we just did that derivative with this u thing, we also have to attach the derivative of whatever u is. Now in here, I'm going to substitute the x squared back in for the u. So this is going to say the cosine of x squared, but now I need to look at what the derivative of that u thing is. So if we know that u is x squared, then the derivative of u is just going to be 2x. So I'm going to replace the du dx with that 2x. Now I'm actually going to pull that 2x to the front, so I'm going to write this as 2x cosine of x squared. Now there's a few other things that we could run into, All of those examples that we've done so far have had the x variable being the upper limit of our integration, but in this example we're looking at what happens if x is the lower limit of the integration. So we're going to try to find dy dx for the equation y equals the integral of 3t sine of t dt from x to 5. So we're doing the derivative, we're doing dy dx of this integral 3t sine of t dt from x to 5. Well, we had a property of integration that said if we want to flip around the order of the upper and lower limits, we're allowed to do that, but we have to take the opposite of whatever answer we get. So this is going to be the opposite of dy dx of the integral of 3t sine of t dt, but I'm going to flip-flop the order on those upper and lower limits. So it was x to 5, now it's 5 to x because we took that negative out in front. So now we can do the derivative of this integral like we've been doing. So the derivative and the integral are going to cancel each other out, and we're going to replace those t variables with that x upper limit, but I need to keep the negative in front. So this will say negative 3x sine of x. Now in this example, we've actually got variable upper and lower limits. So we're going to try to find the derivative, dy dx, if y equals the integral of 1 over 2 plus e to the t dt from 2x to x squared. So I'm going to write this out like we've been doing. We're doing the derivative, dy dx, of this integral. We've got 1 over 2 plus e to the t dt, and we're going from 2x to x squared. Now everything that we've done so far, we've got it so that there was a numerical lower limit and a variable upper limit. So the first thing we're going to have to do is actually use a property of integration to split this singular integral up into two separate integrals. So we're going to split this up, and the easy kind of number to split things up at is 0. So I'm actually going to make an integral go from 2x to 0, but then I'm going to make a separate integral go from 0 to x squared, and what we're going to end up doing is adding those things together. So it's going to be the derivative of our integral going from 2x to 0 of that 1 over 2 plus e to the t dt plus that derivative dy dx of the 1 over 2 plus e to the t dt, but now we're going from 0 to x squared. Now again, we want our lower limit to be the number and our upper limit to be the variable. So this first one, I'm actually going to have to flip those upper and lower limits around. So I'm going to make that negative dy dx of the integral, but now I'm going from 0 to 2x. I flip-flop those around by taking the negative out. 1 over 2 plus e to the t dt, plus we've got that dy dx of the integral from 0 to x squared of 1 over 2 plus e to the t dt. Now notice on those upper limits, we don't just have regular x's in there. So as we do the derivative of this integral, we're going to have to remember to do our chain rule, attach the derivative of that upper limit value. So in here, in this first part, the derivative and the integral are going to cancel each other out. So we get negative 1 over 2 plus e, get rid of the t variable, and replace it with the upper limit. So that's e to the 2x. But now, because we don't just have a regular x upper limit, then I have to attach the derivative of that upper limit to x. And the derivative of 2x is just 2. But now I have to add on. Here, the derivative and the integral cancel each other out again. So we get 1 over 2 plus e, get rid of the t variable, replace it with the upper limit. So this is going to be e to the x squared. But then we have to attach the derivative of that upper limit. So the derivative of x squared is just 2x. Now we can clean this up a little bit. In this first fraction, if I put that 2 over 1 and then multiply these fractions together, well, across the top, we've got this 1 times the 2. I'm also going to attach the negative. So we've really got negative 2 over 2 plus e to the 2x, plus same thing back here. If I take that 2x, put it over 1, multiply the tops together, then we get 2x over 2 plus e to the x squared. That's going to be it for this video. Thanks for watching.